Thank you very much for joining. This is Leandro Mora, and this is the lecture about consistency levels. In the second lecture of this course, we studied the consistency property. We said that a database is consistent if all the operations performed on it are valid, which means that they accomplish the constraints defined by its data model. This property ensures that any transaction will bring the database from one valid state to another valid state. So now the question is, what does a consistency database guarantee? It guarantees that any transaction started in the future necessarily see the effects of other transactions committed in the past. It guarantees that the database constraints are not violated, particularly once a transaction is committed. And it guarantees that operations in transactions are performed accurately, correctly, and with validity with respect to application semantics. Now, let's think about this. In a distributed system, what does consistency imply? Let's see the draw that we have here. A distributed system maintains copies of its data on multiple machines in order to provide availability and scalability. Much better now. When an application makes a change to a data item on one machine, that change has to be propagated to other replicas. Since the change propagation is not instantaneous, there is an interval of time during which some of the copies will have the most recent change, but others won't. In other words, the copies will be mutually inconsistent. Now let's define an important concept: eventual consistency. The term eventual consistency is simply an acknowledgement that there is an unbounded delay in propagating a change made on one machine to all the other copies. Eventual consistency is a consistency model used in distributed computing to achieve high availability that informally guarantees that if no new updates are made to a given data item, eventually all accesses to that item will return the last updated value. A system that has achieved eventual consistency is often said to have converged or achieved replica convergence. Eventual consistency is not meaningful or relevant in centralized systems, since there is no need for propagation. Now, there is a trade-off that we really have to pay attention, and this is availability and consistency. Let's see the draw again. On one hand, we may have a high availability system with eventual consistency. Some systems make trade-offs that favor performance, potentially at the cost of reading stale data. In some systems, the machine where the change is originated first will simply send asynchronous and possible unreliable messages to other machines. Look at this. And declare the operation as successful. This is fast, but at the cost of potential data loss if a machine fails before receiving the update. Imagine that. This machine fails, this machine is not going to receive the update. On the other hand, we may have a consistent system without high availability. in these kind of systems, the machine sends synchronous messages to all other machines. The master node sends synchronous messages to all other machines. It receives an acknowledgement, and only then, when the acknowledgement is received, then it responds to the final users. This system favors consistency and availability at the cost of performance, because you have to wait till you have the answer of all the nodes. Here, I put the same concept so that you can compare both. And we have other question, which is really important. What if in your application, you can relax consistency in some cases, but not in others? In that case, some system, not all of them, some system let the application designer choose how changes are propagated. In particular, if the application is likely to read a data item shortly after it has been changed and wants to ensure that the reader gets the most recent value, then fast propagation is important. In other cases, it may be okay to relax the constraints on change propagation in order to gain performance benefits. For example, if the application is simply capturing data, you are just writing data, then it is acceptable to relax the preparation guarantees in favor of higher write performance. But what if I can't choose and the NoSQL database that I have to use, or that I was told to use, only guarantee eventual consistency? Well, in that case, you have to pay a lot of attention, because when choosing a NoSQL system, it is important to understand where a choice of consistency policy is available. If the database system only supports eventual consistency, then the application will need to handle the possibility of reading stale, which means inconsistency, data. This is not as easy as it sounds, since the responsibility of avoiding the stale read problem associated with eventual consistency is left to the application developer. And this is one of the decisions that may determine the selection of a NoSQL database. Now, let's see an example. Apache Cassandra is a NoSQL columnar database. And one of the features that it provides is the tunable consistency. Cassandra extends the concept of eventual consistency by offering tunable consistency. For any given read or write operation, the client application decides how consistent the requested data must be. Consistency levels in Cassandra can be configured to manage availability versus data accuracy. Consistency among participating nodes can be set globally and also controlled on per operation basis. For example, write or read using Cassandra's drivers and libraries. And here we can see some examples on the type of consistency levels that Cassandra provides. But let's go deeper. Let's talk about write consistency. Replication factor determines in how many nodes the data must be stored, And the consistency level, the write consistency level, determines how many nodes, how to respond with a confirmation message before answering to the user that the operation was committed successfully. So let's see this operation. In this case, the user want to write a specific register on this Cassandra cluster. So it tries to read to write on node 2, and node 2 is going to send the register to node 1 and node 3. For some reason, the node 3 could not perform the write operation, but no one could. As the consistency level is 2, this means that it only needs 2 operations to succeed in order to return a succeed response to the user. For that reason, the operation is completed and the user gets a successful message. Then here we got other example, the read consistency. The read consistency level specifies how many replicas must respond to a read request before returning data to the client application. Cassandra checks the specified numbers of replicas for data to satisfy the read request. Imagine that in this case, the replication factor is 3. So the data, each piece of data, each register must be in at least 3 nodes, and that the read consistency level is 3. Now think about how this operation can be successful. So the user is going to try to read a register from the Cassandra cluster. The Cassandra cluster, the node 1, is going to send a read message, a read operation to the other nodes where the data is stored. Then each node is going to check if the register exists, and it is going to return the result with the timestamp of the insertion of that message to node 1. And then node 1 is going to compare the timestamps to check that all of them are the same version of the register. And if the result is the same, then it will retrieve the user the register that he is looking for. Thank you very much for joining the lecture of consistency level, and well, hope you see you on the next session. Thank you very much.